All right. Good afternoon, class. Our first plan of the day is just jump straight in. We are looking at textbook section 1.6a. Now, as I discussed when we talked about the syllabus, uh, you're going to be able to find the same stuff we talk about today in the Learn section of Hawk's Learning, but I realize a lot of times that those online textbooks aren't very clear and it's hard to really figure out what it is they're saying. So the point of these videos is just to go over that material, go over the vocabulary, work through a couple examples, make sure everything's clicking. Of course, I will be hosting a Q&A session for you later in this day that this video is posted. So then we will have that opportunity to go over any other questions you may have in case this doesn't quite make sense to you after this lecture. So, without further ado, let's go ahead and get into section 1.6a. Now, most of chapter 1 is going to be kind of review stuff. A lot of this is going to be things you would have maybe seen in Algebra 1, Algebra 2, but for many of you, maybe you're later in your careers as a college student, and you haven't done this stuff since high school. So it may be a little rusty, but that's the whole point of chapter 1. We're just going to brush off the cobwebs. Once we've got this down, then in chapter 2, we'll start to move into some calculus ideas. So let's go ahead and get started. This is, again, section 1.6a of your textbook. And I want to start with a little bit of vocabulary at first, just to make sure that we're all using the same words, and when we use these words, we mean the same thing. So the first thing we want to talk about is, what is a function? Now, depending on the textbook and depending on the class, you may get slightly different definitions. For the purposes of this class, we're going to say a function, if we have a function f, then f is a mapping that matches each x in some set D. Now we'll talk about what D is in a moment. That's going to be our domain. But we're looking at each x in D, and this x is being matched with exactly, that matches each x in D with, and this is important here, exactly 1 y in R, where R is going to be our range of the function. Now, this point here about it mapping to exactly 1 y, so for any given x, you plug into a function, so f of x is equal to 2x. This is an example of a function. For any given x that I plug in, it will only output exactly 1 y. So if I plug in f of 1, then I can only ever get 2 out of it. I'm never going to get any other number out of it if I plug in 1. And so this keeps this rule, and so we can call this a function. So that's our first definition there. What is a function? Next, we would like to talk about, let's see, now is the black. I've got some other colors here I was going to test, see what comes out, but we'll find out. Let me know if any colors don't look good. All right, so we had this idea of x is in D and y is in R. And we had this example of f of x is equal to 2x. Now, when we plug in numbers into this function, when we have an input, our input, these are going to be our independent variables. So that's our next point here. So for all x in D, x is a independent variable. And likewise, we can say a similar thing for all y in R. Y is now instead of independent, it is a dependent variable. This is because whatever y is that matches with a particular x, that y depends on what x you plug in. So when I plugged in f of 1, that gave me 2. So this y value of 2 depends on what x I put in to get it. So it's a dependent variable. Dependent and independent. So we've already touched on that D we call domain. So D, that's for our domain. It's the collection of points that we can plug into a function. R is our range. It's the collection of possible outputs. So for this particular graph, when f of x equals 2x, then D, well, D is what are all the possible x's we can plug in? Well, for this graph, luckily, since it's a well-behaved line, then I can plug in any x value and it's going to be okay. So our domain is from negative infinity to infinity. Likewise, if we think about what is our range, well, the range is what are all the possible outputs? What are all the possible y values that this function can get to? Well, again, because this line is going to keep going in both directions, to the positive direction and negative direction infinitely, we're going to be able to reach any possible y value. And so again, in this example, the range is from negative infinity to infinity. So of course, this is a relatively simple example here, but as we move forward in the course, we're going to have some other examples where we're not going to have so well-behaved domains and ranges. But we'll get there, so don't worry about it yet. So, as we keep moving forward here, try to give you a second to copy some things down in case you didn't get it. I'm going to try to leave the vocab until we're ready to move on to the examples. So the next thing we'd like to talk about is what is a piecewise function? Now for this, what is a piecewise function? Piecewise function. Now a piecewise function is, well, as you can tell by the name, it's a type of function. But more specifically, it is a function that can be represented by different algebraic expressions used for different parts of the domain. So what does that mean? Well, let me write it down first, then we'll talk about it. So what we're looking at here is f is represented, I can't spell. Is represented with different expressions over different parts of the domain. So let me give you an example so you can kind of see what we're talking about here. For instance, if I have the piecewise function, f of x is equal to 2x if x is greater than or equal to 0, and 0 if x is less than 0. So the whole point of this is telling us we've got two different expressions here. And depending on our input, our independent variable x, if x is a positive number or 0, then we use the expression 2x to find our y. If x is a negative number, then we just say, okay, y is 0. And so this is the algebraic representation of a piecewise function. But in order to see how this looks graphically, I've got Desmos over here on the side for us. I can just pull it up for a moment. So here we have the piecewise function. And as you can see here, when we have x is equal to 0, then, well, 2 times 0 is 0. And so we have a point at 0, 0. But for x greater than 0, then we have this y equals 2x line take over. And so for x greater than or equal to 0, we have this on the right side. However, here on the left, when we're dealing with x that is negative, x that is less than 0, then we have the horizontal line y equals 0 take over. And then this holds true for any x that is negative. So the whole point of this graph and showing you what this looks like is to really get at, what is the point of piecewise functions? And that is to be able to take different functions that maybe graphically look different and be able to stitch them together at any number given of points that you may want to have them connected for. And this is especially going to become important once we start dealing with some more complex problems where maybe a single expression is not going to be able to accurately describe the problem for every case. And in the event where that happens, then we have to use piecewise functions, where maybe for different values of x, different expressions hold true for our problem. So that's the point of this. This is why we're looking at piecewise functions. And the main goal of this really for 1.6 is just to refamiliarize you guys with some of these terms that maybe it's just been a while since you've seen. And there you have it. So let's go back to the board. Cool. So back to the screen. Now, right, we covered piecewise functions. The last definition I'd like to cover for 1.6a is something called the vertical line test. Now, this has to do with our definition of a function we have written up above. So I'm going to assume you guys probably have these other definitions copied by now. I'm going to go ahead and erase those. And the vertical line test, says vertical line test says that if you can draw a vertical line anywhere that crosses your graph at multiple points, then it is not a function. Now, what do I mean by that? Well, if you think about, if I graph something that looks like this, and maybe it looks like a sideways parabola. So it kind of goes out this way, then it goes out this way, and maybe at x equals 1, then I have a point at 1, 2, but I also have a point at 1, -2. Now the problem with this is that it violates our definition of a function. Remember where our function definition says it is a mapping that matches each x in our domain with exactly one y in R. So in this case, if I plug in 1 for this function, well, I can get two different y values. I no longer have exactly 1 that x matches with. And so, because I can draw this vertical line on the graph, it fails the vertical line test and is therefore not a function. This is going to be relevant when sometimes maybe you'll have a graph of something, but you won't have the function per se, and you're trying to tell if it is a function or not. Well, if it fails the vertical line test, then it is not a function, and then you can keep going along. So, that covers our vocabulary for 1.6a. So now I'd like to do a couple examples before we move on to 1.6b. Oh, I hope we're still recording. Okay, good. It's still in progress. So, right. Examples. Right. So for this very first example, the main goal is really to just, again, get familiar with what functions look like and what it means to plug stuff into it and how we go about doing that. So for this first question, we want to know what is f of -3. So we just plug in -3 for everywhere we see an x. So we have 3 times -3 squared minus, now be careful to make sure you keep this negative on the outside. So we've got minus -3 plus 2. And so now we can work through the algebra. Well, -3 squared, negative times negative is positive. So we've got 9. When you minus a negative, double negative is a positive. So we've got plus 3 plus 2. Now 3 times 9 is 27, plus 5, and so we get to our final answer of 32. And just as a further demonstration, if we do the same problem with f of 2, then we plug in 2, we get 3 times 2 squared minus 2 plus 2. Now lucky for us, the minus 2 and plus 2 cancel out. So we've got 3 times 4 is going to give us 12. And again, we've found our answer. Now this last one may look a little foreign, but this is going to become important later, I think towards chapter 3 when we start talking about derivatives. So when we have this f of x plus h, now just like we did these other problems, whatever is on the inside, this is your input, and you're going to put it wherever you see an x. So in this case, when we have x plus h, you want to make sure you keep this in parentheses. So we've got 3 times x plus h, quantity squared, minus, parentheses, x plus h plus 2. And then from here, we just work through the algebra. So we have 3 times, when we square this, we square the first term, x squared, double what you get when you multiply them together. So plus 2xh squared the last term plus h squared. Now here we can go ahead and distribute our negative into our parentheses. So we've got minus x minus h plus 2. And so we keep going. We can distribute our 3 in. And we've got 3x squared plus 2xh plus h squared minus x minus h plus 2. Oh, I'm sorry. This should be a 6. 3 times 2 is 6. Yeah, 3x squared plus 6xh plus, and I should have a 3 here, plus 3h squared minus x minus h plus 2. Now, unfortunately, without knowing what x and h are, this is as simple as we can write it. And so that's our final answer. So as ugly as it may look, it's alright if you get answers like this when we start plugging in these other kind of things that aren't so well defined. And again, this is going to be more important later when we get into derivatives in chapter 3. Alright, so those are the examples I wanted to cover. Right, there was one more example I wanted to go over before I move on to 1.6b. Alright, now this last example is, as we discussed earlier, when we're looking at a function, sometimes the domain and range are very well behaved and easy to define. Other times, it's not so obvious. So I'd like to take a look at this example. F of x is equal to 3x divided by, I want to make sure I copy this correctly. Yeah. 2x squared minus 8. Now, here we have an expression with x divided by another expression of x, two different expressions. Now, the whole concern here is when we start talking about what is the domain, well, the question really is, what values of x can we plug in? Or what values of x can we not plug in? And the question here is more about what x's we can't plug in, because if I were to plug in some x that would create a 0 in the denominator, then I would have 3 times whatever that x was, I'll call it x prime, that makes this denominator 0, then I would have a number divided by 0. Now, obviously we can't do that because this is undefined. If you type in your calculator 3 divided by 0, you're going to get an error. So we want to avoid things like this. Now, in order to do that, we need to find out, where does this happen? We want to know where these, I like to call them problem children. If we can find where 2x squared minus 8 is equal to 0, we'll be able to find the problem children for this equation here. So we set this equal to 0, and we've got 2x squared is equal to 8, divide by 2, and then take the square root. Now remember, when we take the square root of 4, we get two different answers here. We get plus or minus 2, because if we have negative 2 times itself, the negatives are going to cancel. So we actually have two answers here for x that create a problem. So what does this tell us? Well, as far as our domain goes, so x cannot equal 2 or negative 2. Because if it did, we would have a domain, or we'd have a 0 in our denominator. So we want to avoid that. So then we move on, and when we talk about our domain, this tells us our domain can be anything except for these two guys. So then that's it. We just have to write this in set notation. So I can plug in any negative number up to -2. I can't include -2, so I do a soft parenthesis instead of a hard bracket. Union, that means I'm including multiple sets here. Now I can plug in any number between 2 and -2, so long as I don't plug in those numbers. So I've got, again, soft parentheses. And then we union from 2 up to positive infinity, because I can plug in any positive number larger than 2. And that's it. That's our domain. So that gives us an example where the domain can be less behaved. And so these are things to watch out for, especially when you see fractions. You want to make sure you don't make the denominator 0, and so you want to exclude those points where the denominator will equal 0. Okay, so that covers 1.6a, and that should get you through everything you need on Hawk's Learning. Of course, if anything is still not working out, or if any of the questions you're looking at on Hawk's Learning just don't seem to be working, even if you think you're putting in the right answer, then I believe Hawk's Learning does have a button where you can alert instructor and let them know, like, hey, this question I think is bugged. I'm doing it correctly, but it's saying I'm wrong. I'll get an email for those questions, and then I'll be able to check them. If you're right, then I can give you full credit, and if you're not, then that may be able to help us figure out, where you're going wrong in your thinking, and we'll be able to help you figure out how to do the problem correctly. So, with that being said, that covers 1.6a, and we are ready to move on to 1.6b. So, again, for 1.6b, I'd like to cover some vocabulary, so we're using the same words, and then we'll move into some examples. Now, this first thing we'd like to talk about is, what is vocabulary? Okay. What is function composition? So, function composition is when you compose two functions, or in other words, it's when you put a function inside of a function. So, what does that mean for us? Well, if f and, say, g are functions, then the function composition, which is written as f, now you want to watch out for this in your homework. It's going to be an open circle. This is not multiply. This is not multiplication. If you see an open circle that is not filled, this means function composition. So this means f composed with g. Or in other words, you can think of this as f, and when you see that O in the middle, think f of g. If you remember this of trick whenever you see an open circle, that's going to save you a lot of trouble with remembering which way this goes when you see it. So when you see f composed with g, or f of g, then this is written as f of g of x. Now, what does that actually mean? How does this work out? Well, we can do a quick little example. If I have f of x is, say, equal to x plus 1 quantity squared, And then let's say g of x is equal to, let's say, oh, sorry, I overcomplicated the problem. Let's say f is equal to x squared. And then we'll say g of x is x plus 1. Now here, when we calculate f of g, or f of g of x, then just like before when we had that x plus h example, you take whatever is here on the inside, and you're going to plug it in for function f. So g of x is x plus 1. So you want to make sure you wrap that guy in parentheses, and we're going to plug him in wherever we see an x in f. So f of g of x is going to be this guy plugged in, and then we're going to square it, because that's what f does. Well, now when we write this out, then we're going to get square the first term. X times 1 is x. Double it. That's going to give us 2x. Square the last term. So we've got x squared plus 2x plus 1. This is f composed with g. So this is function composition along with a little example. Now, something to be careful of, this next point here is, in general, f composed with g does not equal g composed with f. This is not a commutative operation. F of g is not necessarily going to equal g of f. Now, you might find some examples where it does happen. I'm not saying this is impossible. What I'm saying is that in general it is not true, and so you shouldn't assume this is true. And our previous example here actually is a good example of this. So we have f composed with g written out over here. If instead we try to calculate g composed with f, then this is g of f of x. Now f of x is x squared, so we're going to plug that in wherever we see an x in g. So then g is equal to x squared plus 1. G of x, I mean. But you can clearly see that these two equations are not equal. So this just goes to show that f composed with g is not equal to g composed with f in general. And again, you may find some examples where it does happen, but they're rarer examples. They don't happen all the time. So just be careful of that and make sure you don't assume that. All right. So moving on with our vocabulary. Right, we want to talk about slope. So you may remember from high school days when you took Algebra 1, or perhaps you took Algebra 1 here at UNC Charlotte or a different university and you transferred. Either way, you may be familiar with the equation y equals mx plus b. This is our general format for a linear equation. Now, m here, as you might have guessed, this is our slope. Now, b is the y-intercept, but we're not so worried about that for the moment. But what is slope? Well, another thing you may have heard in high school, or maybe one of your other previous professors may have said, slope is rise over run. If we go back to our example of f of x is equal to 2x, and we graph this, so at 0, we're 0. 3, 4, 5. If I plug in 1, then I'm going to get 2. If I plug in 2, I'm going to get 4. If I plug in 3, I'm going to get 6, and so on. So I've got this line here. So the slope in this example is 2, but this also tells us what the rise over run is. If you're trying to find the next point on this line, it rises by 2 and goes over 1. It runs 1. So this is our one way that if you have a graph, you can find out your slope if you have 2 points. It's how much you rose between the 2 points divided by how much change in x you have. So this is rise over run. Now another way to think of rise over run is the rise is your change in y. How did you change in the y direction? Whereas your run is your change in the x direction. Now, because it becomes a headache to write change in over and over and over again, mathematically we just write this as delta. That's what this triangle is. Delta y divided by delta x. And this just represents change in y divided by change in x. Now, how do we calculate change in y and change in x? Well, again, if I have 2 points, let's say x1, y1, and x2, y2, this is point 1, point 2, then the change in the y's I can get just by subtracting and find the difference. So y2 minus y1 will tell me how much it rose between these two y values. Now it's possible when you do this subtraction you'll get a negative number, in which case that tells you that when it rose, it actually went in the negative direction. So sunk is a better word, but we can also just call it negative rise. And then the same thing for change in x. This is x2 minus x1. Now this concept is going to become very important when we start talking about slope and talking about derivatives and the slope at a particular point. But we'll get there. That's down the road in chapter 3. So that's our change in x, our change in y. We've covered our slope. Right. And then the last thing to note here is if we're not sure what these y values are, maybe we only have the x's, well, these y's are the y's that pair with these x's, that match with these x's on whatever function it is we're looking at. So another way to write this is f of x2 minus f of x1, since that'll give you the corresponding y value, and you divide that by x2 minus x1. And so there you have it. That's a more formal definition for slope. However, this representation here, there's another name for it, and this is called the difference quotient. Now, the difference quotient, as far as this particular calculation, isn't going to be as big of a deal later in the course, but for the sake of Hawk's learning, if it asks you questions like what is the difference quotient for these 2 points, then this is what it's talking about. This is the formula you want to use. And again, the difference quotient, this is just another representation for slope, and that's going to be very relevant as we get into derivatives later in chapter 3. So, with that being said, that covers our vocabulary for 1.6b. And now I'd like to take a moment to go over a few examples before I finish up this lecture for today. All right. So we'd like to talk about some examples now. Now what we have here for our first example, I see. Okay. So we've got two examples we want to work through before we close up. This first one is, suppose we have f of x is equal to 4x squared minus 2x. Well, then the question is, we want to find f of x plus h minus f of x. We want to find out what this is. Now, like we saw in our examples for 1.6a, when we see this x plus h business, just wrap it in parentheses and plug it in wherever you see an x up here. So this guy is equal to, take x plus h and plug it in. So we've got 4 times parenthesis x plus h squared minus 2 times parenthesis x plus h, and then minus f of x. So minus f of x, you want to make sure you distribute the negative here. So we got minus 4x squared plus 2x. And there we have it. Now we can start distributing, working through the algebra, and seeing if we can simplify this any. So we can start by squaring this, and I'll leave the 4 on the outside for now. So we've got x squared plus 2xh plus h squared minus 2x minus 2h minus 4x squared plus 2x. We're going to go ahead and distribute our 4 now. And we've got 4x squared plus 8xh plus 4h squared minus 2x minus 2h minus 4x squared plus 2x. And so we've got it all multiplied out. We can start combining like terms. So we got 4x squared here and negative 4x squared. They're going to cancel out, so I'm not even going to worry about it. We got a negative 2x and a positive 2x. So again, those are going to cancel out, and we don't have to worry about it. So now we just write whatever we have left over, and we've got 8xh plus 4h squared minus 2h. And without knowing what x and h are, this is actually as simple as we can get this. And that's a perfectly valid answer like that. So, again, this is our first example that we wanted to cover for 1.6b. And this particular formatting, why we care about this f of x plus h minus f of x, again, that's going to become more apparent when we get into chapter 3. So don't worry about that too much for now, but definitely make sure that you understand how to do this, because you're going to be doing it over and over again when we get later in the course. So put a pin in that and remember that for sure. And then the last thing I would like to look at, just to make sure we drive home, how function composition works, is if we have the example, f of x is equal to x squared, and g of x is equal to 3 divided by x, then what is f composed with g? Or in other words, what is f of g of x? So again, take whatever is on the inside of this, g of x, and we want to plug it in for f. So g of x is 3 divided by x. We want to plug that in over here. Make sure we keep this in parentheses. So we're going to have 3 divided by x squared. And then remember, when you square a fraction, you square both the numerator and denominator. And so for this, we're going to get 9 divided by x squared as our final answer. All right, so that about wraps up everything I wanted to cover for 1.6a and b. That should hit all of the high points for the Learn section of Hawk's Learning on this section. So this should give you everything you need to be able to complete the Certify section for 1.6a and b. But again, make sure if these examples wasn't quite enough to really get it all solidified for you, then make sure you're going through the practice section of Hawk's Learning. There's, absolutely no negative against you for missing those questions in the practice. That's purely to give you a chance to learn these questions, to figure out how they work, and be able to do them for yourself. If you can get through practice without missing anything, then you should be golden through Certify because it's going to be the exact same questions. All right, well, I hope that helps. Of course, as we discussed with the syllabus, don't be afraid to reach out to me, send me emails, send me questions. We will also have a Q&A later today. We're shooting for 3 p.m., but depending on schedules and whatnot, we can adjust that. However the case, that's it for this video, and let me know if you have any questions. All right, well, best of luck, everybody.